let's look at absolute value inequalities symbolically. For any real number, positive k, then the absolute value of x is less than k if and only if x is between negative k and k. Think about this. We're talking about distance from 0, and absolute values are always positive, so k is positive. If the absolute value is less than k units away from 0, then it can be negative units away, negative k units away from 0, just in the opposite direction of k. But it can't be more than that. If it's more than that, then the absolute value is not going to be less. So for each of these, we'll solve, graph the solution, write the solution in interval notation. And I will remind you of my mnemonic for working on absolute value inequalities. When you're dealing with an absolute value inequality, the absolute value is on the left. Then for less than, we're looking at an and inequality, compound inequality. So if we start out with number 6, absolute value of 2x plus 1 less than 5. Because it's a less than, I can put the expression in the absolute value between negative 5 and 5. Less than is an and inequality, and ands are 3-part inequalities. I can solve this for x. 3-part inequalities, remember, whatever we do to the middle, we have to do to the outsides as well. We're really solving 2 inequalities at the same time. And the goal is to get x by itself in the middle. Divide by 2, negative 3 less than x less than 2. So graphing it, negative 3 to 2 between, not including, and our interval notation directly related to that graph, negative 3, comma 2 in parentheses. Looking at number 7, we can play the same game, less than or equal to 6, negative 6 over on the other side, in the middle, negative 3x minus 2, and we proceed to get x in the middle by itself. At this step, we're supposed to divide by negative 3, but when we divide by negative 3, we have to change the signs of the inequalities. We're not allowed to keep them the way they are, and we've talked before about why that is. So we end up with 4/3 greater than or equal to x greater than or equal to negative 8/3. Graphing this one, negative 8/3 is less than 4/3, so I want to make sure I have them on the correct places on my number line. X is between. This time I have an equal to, greater than or equal to, so I'm going to make those square brackets, negative 8/3 to 4/3 square brackets. Check out number 8. Absolute value of x is less than negative 5. We can consider solving this in 2 ways. The first way, remember that the absolute value always comes out positive. So in this example, how can we have the absolute value of x, a positive number, less than negative 5? We can't have it, ever. So in this case, we can say no solution or empty set, whichever you're okay with. The other way we can consider it, let's suppose we didn't see that at first, and we wrote out what we should. Looking at this, is this right? 5 is less than x is less than negative 5? How can I have 5 be less than something that's less than negative 5? I can't do that. X isn't between them because x has to be less than negative 5 and greater than 5. This doesn't work. This is a poorly constructed compound inequality. Remember when we talked about compound inequalities that if we took one thing out of it, the middle, if we removed the middle, the remaining inequality still has to hold. And 5 is not less than negative 5. So we still have no solution or an empty set. Be really careful when you're working with negative numbers, with inequalities and absolute values. Let's take a look at another problem. This is number 13. 3 plus the absolute value of 2x plus 1 is less than or equal to 7. Before I can turn this into its corresponding compound inequality, I have to make sure I have only the absolute value isolated on one side. So our first step here will be to subtract 3 from both sides. We need the absolute value to be by itself on one side of the inequality or equation before we make the transition of removing the absolute value symbols. Here, if the absolute value is less than 4, then it will also be greater than or equal to negative 4. Whatever's inside that absolute value gets copied over, only the inside. And then we will proceed to get x by itself in the middle. And if we divide by 2, we're not dividing by a negative, so things are okay so far. And we're left with negative 5 halves less than or equal to x less than or equal to 3 halves. And we can graph it. Negative 5 halves and 3 halves. Doesn't have to be fancy. Less than or equal to's. The equal to's will get us brackets and x's between them. And we have an interval answer of negative 5 halves to 3 halves, including the endpoints. Let's look at the greater than inequalities for absolute values. I still have a positive k. If the absolute value of x is greater than k, then x must be greater than k, or x must be less than negative k. Goes along the same reasonings we had before. Distance is always positive, absolute values are always positive, and since it's a distance, if we're greater than k units away from 0, it can be negative k units away or greater in the opposite direction. And this all relates back to those graphs. The greater thans for these absolute values were the tails that were going off into infinity. The same thing's happening here. Just like before with our less than, this absolute value of x greater than k, we have another mnemonic that can help us. We need to make sure the absolute value is on the left, and then the greater thans, or greater, corresponds to or compound inequalities. So we'll be using ors for the greater than absolute value inequalities. Looking at number 9, absolute value for x minus 3 is greater than 9. We know we have an or inequality because it's greater than. And so I'm going to have two separate inequalities for an or. I will copy it all over exactly as it is, but take out the absolute values. And then for the second one, I copy what's inside the absolute values. I change the direction of the sign and the sign on the number. Both of these things have to happen. Because we're talking about an or inequality, we've got to be less than the negative in order for the distance to be greater. So make sure you keep that in your mind. We change the direction of the inequality and we put a negative on the number. And then we solve them just like we solved ors. So we need to get the x by itself on one side, divide by 4. 6 divided by 4 will give me 3 halves. This is an or statement. We've got 3 and 3 halves. X is greater than 3. X is less than 3 halves. And that gives us our inequality. Our inequality, negative infinity to 3 halves, 3 to infinity. If we try number 10, the absolute value of negative 2 minus x is greater than or equal to 9. So first step is to copy it over, but leave out the absolute values. I know this is an or because my absolute value is to the left, and it's a greater than, so I have an or. Negative 2 minus x. Switch the direction of the inequality. Change the positive number to negative. And then we've got to get rid of the negative for the x. So we could multiply by negative 1, but if we multiply by negative 1, we have to change the direction of the inequality. And an or between them, because we're doing an or, we have negative 11 and 7, less than or equal to negative 11, greater than or equal to 7. And we get the inequality negative infinity to negative 11, including negative 11, union 7 to infinity, including 7. Taking a look at one more, absolute value 7x plus 2 greater than or equal to negative 5. There are two ways to think about this one. The first way to think about it is the intuitive way. We have a positive number and a negative number, and I want to know what x values can I have so that a positive number, a number that's always going to be positive, is greater than or equal to a number that's always going to be negative. Positive numbers are always greater than negative numbers, so this is going to turn out to be all real numbers, or negative infinity to positive infinity. That's one way to solve it, but let's suppose I don't see it. Suppose I don't see that right away, positive number greater than or equal to a negative number, and I try to do it using the techniques from before. So we'll start out and copy everything out except for the absolute values, 7x plus 2, and this time I'm going to change the direction of my inequality and change the sign of the inequality. And we try to solve it, and we get x is greater than or equal to negative 1, or x is less than or equal to 3/2. I'm going to graph in two different colors. So we have negative 1 and 3/2. X is greater than negative 1. Greater than negative 1. And I'm including negative 1 on that because of that equal sign. And then x is less than or equal to 3/2. Now looking at the graph, an OR inequality says we take everything that's colored, whether it's colored once or it's colored twice, we don't care, it's been colored, we take it, we claim it. Everything's colored. So our answer is all real numbers, which we already knew that when we thought about the intuitive way of solving above. I say this to you in a caution. Be very careful when you're solving these so that you pay attention to whether you're doing an AND or an OR. And make sure that you're selecting the right parts. An OR inequality takes everything that's colored by both inequalities. We take it all, one or the other or both. But an AND inequality only takes what's double colored. And you see in this graph, we have a chunk that's double colored between negative 1 and 3/2. But I don't want to just take that because I don't have an AND inequality. I have an OR. So again, pay attention to those details. I know it can be tough. Mathematics is very precise. I've got two more quick examples for us with the greater than. In number 14, we've got a fraction, absolute value 3x plus 4, all over 5, greater than 1. Whenever we've got fractions, we need to get rid of the denominator. Multiply by 5, we get absolute value 3x plus 4, greater than 5. Now that I have my absolute value isolated, I now can use the corresponding compound inequality to solve this absolute value. I notice I have absolute value, inequality symbol, number. So this symbol here being a greater than means I'm looking at an OR inequality. So copy it over, 3x plus 4 greater than 5, or 3x plus 4 less than negative 5. Change the direction of the inequality symbol, change the sign on the number. Then solve for x. And we get x is greater than 1/3 or x is less than negative 3. I can graph that. Negative 3, 1/3. X is greater than 1/3. X is less than negative 3. We get negative infinity to negative 3, 1/3 to infinity. And then one more quick one. At first this looks pretty innocent. We need to divide by negative 4. Remember that when we divide by negative 4, we change the direction of the inequality. And now we have the absolute value of x plus 1 is greater than negative 5. Absolute value is always positive, so we have a positive number greater than a negative number, and this is always true. So our solution is all real numbers.